Hello everybody, welcome to Nature Live Online. My name is Alistair and I'll be your host for today's show. It's lovely to have you here. Thank you for joining us. If this is your first time logging on to watch us, thank you for coming. Let me tell you a little bit about what Nature Live is all about. This is an opportunity for you to meet and speak to some of the scientists that work behind the scenes at the Natural History Museum in London, carrying out groundbreaking research and working with our wonderful world-class collection. The show is live, so if you do have any questions for my guest today, please feel free to pop your questions in the chat and we'll do our best to get through as many of them as we can during the course of today's show. As you can imagine, it's been a really tough year for the museum and for many cultural institutions all over the world as a result of the COVID-19 pandemic. So if you are enjoying the show and would like to support us, please do consider a small donation. Any amount, big or small, is greatly appreciated, and it will really help us out as we've been losing a lot of vital income this year as we've been unable to open our doors for much of the past year. So thank you very much for any donation that you can give. Now, my guest today is Tom Matthews. He is a PhD student at the museum in London, and he works in the field of mining. He's looking at metals and minerals, how we find them and locate them, and how we get them out of the ground, and how do we rely on them and depend on them for our modern lives. So Tom, thank you so much for joining us today. How are you?
I'm very well, thanks. How are you?
Oh, it's great to have you. I'm really good, thank you. And I'm really excited to be talking to you today because I think this topic is something that I have to admit I hadn't given a huge amount of thought to in the past. And it's really, really fascinating to learn a bit more about the whole world of mining and how it's going to help us in some ways achieve a greener future, which might surprise some people at a first glance. So yeah, I'm really looking forward to chatting to you today. So thanks for joining us. So just before we dive into the topic, can you tell us a little bit about sort of what you do at the museum, what your role is?
Yeah, so I'm a PhD student based at the Natural History Museum and Imperial College London. I research how ore deposits form and in particular how copper deposits form. And in my research, I use the chemistry of rocks and minerals to aid mineral exploration, so looking for ore deposits. And my PhD is in partnership with Rio Tinto.
Brilliant. So is this something that you've always been interested in, you know, sort of rocks and mining and that kind of thing?
I would say that my interest in geology first started at school. I was lucky enough that my school offered a geology degree, geology GCSE. And at that time, I was most interested in fossils. My interest kind of carried on, and I decided to do a degree in geology, which I did at the University of Leeds. And it's there where I'd say my interest in ore deposits first started.
Excellent. Have you ever been to a mine yourself?
Yeah, I've been to quite a few, yeah.
Yeah, because I remember when I was a kid, I took a visit to a coal mine in the north of England, and I remember picking up a piece of coal and throwing it on the ground, just not even thinking, you know, not really caring about it, not thinking about it. And the guy that worked there came up and he told me all about it, and it did kind of spark my interest in it. Because until that point, I never really considered where this stuff comes from or how it works. So yeah, it's I think for a lot of people it's not somewhere they would typically go to or have experienced before. Now you've mentioned that you obviously you're part of the museum and Imperial College. You work with Rio Tinto as well, and there's a centre at the museum, isn't there, that's actually focused on kind of looking for deposits of minerals that we're interested in, isn't there?
Yeah, so our research group is called the London Centre for Ore Deposits and Exploration, and we're a research group based at the NHM. And our research focus is using the chemistry of rocks and minerals to understand ore deposits and in order to develop more efficient and more environmentally friendly ways of locating ore deposits. And we work a lot with industry partners, and we have researchers at several different stages of their careers. So we have master students, PhDs, right through to postdoctoral researchers and research leaders as well.
So a lot of work going on there. Now, a few of the terms that you've used already, you've talked about sort of minerals, ore deposits, metals, and things. Just so that all of our viewers know where we're at, could you sort of explain a few of those to us and how it relates to what we're going to talk about today?
Sure. So first we'll think about elements. So these are simple chemical substances that can't be broken down further using chemistry. Now these may be elements like oxygen or carbon or copper, and elements combine to form minerals. So when we're thinking about ore deposits, so these are accumulations of minerals in the Earth's crust in economically viable quantities. And these may be deposits of metals, so gold or copper, or non-metals, so things like diamonds. And on screen here, we can see just a typical rock that we might see in the Earth's crust. And the key difference that separates something like this from an ore is simply the concentration of the element that we're interested in. So if we take gold, for example, this rock may contain around maybe 1 part per billion gold. So that means that there's 1 atom of gold for every billion in the rock. So incredibly small. And if we were to use an analogy for how much this actually represents, if we took this rock to be like a blue whale, so think of Hope the whale that we have in the museum, then the amount of gold in that rock would be equivalent to the size of a pea. So incredibly small.
Wow. So if you've got if you've got a rock the size of a blue whale, then the example you're saying here is the amount of gold in that rock would be the size of a pea. Like exactly. That's incredible. It's no wonder it's a precious metal.
Yeah, exactly. Whereas if we were to think of an ore instead, so here we have an image of some gold ore from Namibia. I mean, this may contain around 5 parts per million gold. So 1,000 times more than we had in our typical rock. And again, if we revisit that blue whale analogy, this would be equivalent to the volume of a football. So a little bit bigger, but still, really small compared to the blue whale. And then when we think about mining, so mining is the process of taking our ore, digging it out of the ground, and then turning it into a pure product. So this could be things like gold bullion, for example. And here we have some gold bullion bars on the screen.
And just based on what you've said, it's the amount of gold that we see in that picture, for example, thinking back to what you're saying, a blue whale-sized rock would have a pea amount of gold, say. That's an awful lot of rock we've had to dig up to get that kind of gold. And what's in that picture is in and of itself just a tiny representation of gold, isn't it?
Yeah, exactly.
Yeah, incredible stuff. So let's look at like people. I'm sure people will have images in their head of mining and what it looks like. And sometimes we've got to dig up very big holes to get access to enough of the minerals that we're interested in. Let's take a look at that, because the scale of this is quite incredible sometimes, isn't it?
Yeah, exactly. So here we have an image of the Chuquicamata mine, which is in the Atacama Desert in Chile. And I've been fortunate enough to actually visit this mine, and it's incredibly large. It's actually one of the largest man-made holes in the world. And just to kind of give you an indication of just how big this thing is, on the right we have an image of the Burj Khalifa, so the tallest building in the world. And the pit at Chuquicamata is in fact so deep that we could fit the whole of the Burj Khalifa inside of it. So, these are incredibly deep holes sometimes. And we can also, I'm not even sure that you can make it out, but at the bottom of the pit, there are these tiny, tiny dots. And these are actually mining trucks. And these things transport ore from the bottom of the pit through to the processing plant. And I mean, when we look at them compared to the size of the mine, they look tiny. Whereas when we compare them to people, I mean, these things are actually really, really big. And it just goes to show how big these things actually are.
That's incredible. Yeah, I mean, the sort of the technology on display there is immense. the size of the tires on that truck alone, and some of the machinery that you find in some big mines really it's on a different scale to what we're used to seeing in everyday life, isn't it?
Yeah, some of it is incredibly large. So on screen now we have a picture of a bucket wheel excavator, and on the right hand side at the bottom we have a wheel, and we have several different buckets attached to that wheel, and this is rotating round and scooping material up from the earth. And these things again are incredibly large. So one of these actually has the Guinness World Record for the heaviest land vehicle of all time. And I believe that from bottom to top, these things are about 100 meters, which is about equivalent to the size of Big Ben. Now, I don't know about you, but I personally can't imagine something the size of Big Ben driving around.
That's immense. I mean, do you know what? Looking at it, it looks like something out of Thunderbirds to me. It's like it looks like something kind of made up that it wouldn't actually be able to move if you actually made it. But I guess the point is, it doesn't have to go very fast. It's built and works within the setting that it's designed for. Now that sense of scale to really kind of hammer it home for anyone that's been to London or for our UK viewers, they might appreciate this comparison. So if we look at a map of central London. In particular, we can look at the area of London, South Kensington, where the museum is, which is highlighted in the red box at the bottom of the screen there. That green outline represents the outline of the pit that we just saw in the screen a little bit earlier. Is that right, Tom?
Yeah, exactly. So this is the outline of the Chucky Kamata pit, overlaying over parts of central London. So, like you said, we've got Hyde Park in the centre there. And if this thing were in central London, this would be running from kind of Kensington and South Chelsea up through to Paddington in the north. So this would take up, a significant portion of central London. These are very big things.
Yeah, and of course it's deep as well, which we don't have represented on the schematic here. But do we also dig? I remember, as I said at the beginning there, I remember visiting a mine when I was a little kid, and it was a tunnel. It was a tunnel going into the ground, and you couldn't see any of it unless you were standing right at the entrance and walked in. Does that kind of mining still happen? Is that still a form, or is it all these kind of open pits now?
Yeah, so you're right in saying, before we've just been talking about open pit mines, but you're right in saying that we also have underground mines as well. And indeed, we also have underwater mines, although these are quite controversial. But what determines whether we have a mine at the surface versus one underground is dependent on the geology. So in our Chucky Kamata example, the metal is concentrated in relatively low concentrations across a large area, and it's quite close to the surface. So in that case, it's beneficial for us to mine at the surface, whereas some other mines, so maybe like a gold mine, and I imagine, when people think of what mines look like, this is probably the thing that they're picturing, kind of narrow tunnels leading deep underground, that kind of thing. But so if we have like gold deposits, these might be in like kind of veins, so several centimeters thick, in fact, but in high concentrations, and they may go deep underground, like several kilometers underground. In which case, it's much better for us to just mine underground instead of taking everything out. It's just not cost effective.
Yeah, so I guess it's based on circumstance and the situation that's going on, and the particular thing that you're interested in getting. So we've had a question just come in from Facebook. Thank you very much, guys. Do keep your questions coming, and I'll share as many of them as I can with Tom today. This question comes from Graham, asking, would mining asteroids for precious metals not be less devastating environmentally? Interesting question there. I guess the answer is, in terms of Earth, yes, probably not so good for the asteroid, but really interesting question.
I think this is a topic which is kind of being discussed a lot at the moment, kind of mining in space and on asteroids and that kind of thing. I think a lot of the talk about mining in space is kind of around mining so that we can sustain life elsewhere. So mining like oxygen and things like that on the moon. But I think it would be very difficult to mine metals and things on asteroids. Because if you think of space flight that we have now, a lot of the consideration is around what kind of weight things are. So it's not really practical to try and bring lots of metal back when, you know, weight's such a big consideration.
Yeah, I think that's, at the moment it's still science fiction, but we have to, yeah, we've got to figure out how we can get things on and off the planet more easily before we can realistically, I guess, start mining asteroids for those metals. But I imagine they are rich with resources that if we could, they would be tremendously useful.
Yeah, I mean, it's maybe something to be explored in the future, but at the moment it doesn't seem, it's not viable.
Right. Okay. Excellent. Thanks, guys, for your questions. Do keep them coming, and we'll answer as many of them as we can. But I wanted to kind of touch on, I think at this point it's very easy to think of mining as having this horrendous impact on the environment, and the question that we had there from Graham kind of touched on that a little bit when you talk about the devastation on the environment. These huge pits that are, can be larger than sort of small towns, but there's no denying that we absolutely depend on the material that's coming from those mines. Because is it true to say that we couldn't even be sitting here having the conversation that we are having right now in this form if it weren't for mining?
No, you're exactly right. I mean, these metals are essential for our phones, for computers, for our cars, so both petrol cars and electric cars, and building material. You know, metals are essential to our way of life in the 21st century, and the metals may come from different mines and from different countries as well. And our demand for these metals is only increasing as well.
I can imagine. And take for example something like a smartphone. What sort of metals are in there? Just to give people a sense of that, because I think it's the sort of thing we take for granted, and we've maybe never really thought about it before.
Yeah, so here we have a periodic table. And for those of you who aren't familiar with the periodic table, in the top left, we have our lighter elements. And in the bottom right, we have heavier elements. And it kind of reads like a book. And what we also have is a general progression from more abundant elements at the top down to those that are rarer at the bottom. And what this plot is showing is elements that are typically found in a smartphone. And what we can see straight away is that there are a lot of different elements going into our smartphones. I mean, I think there's around 50 that are noted down on this graph. And the different colors represent elements that are found in different parts of the phone. And what we can also see is that some of these elements are actually quite rare. So if we take the second bottom row, for example, this is a group of elements that we call rare earth elements. So as their name suggests, these are actually quite rare on Earth. Although they're quite useful in terms of lots of different electronics used in magnets and various other things. And obviously you can run into problems where you have elements or metals that are really useful, but actually we don't have a lot of them on Earth.
So that, which actually leads me on to the next question I was going to ask, but where are we getting these from? Because you mentioned quite a few of these are very rare, so I'm guessing they're only found in very specific places around the world.
In some instances, yes. So what we have here is a map showing countries that dominate the supply of a particular metal. And this is problematic because if we think that something were to happen in this country, then the supply of the metal could be negatively impacted. So one example of this is the Democratic Republic of Congo, which produces around 60% of the world's cobalt. Now, cobalt is really important for batteries and things like that. And the DRC has problems in terms of its political stability. And there are also issues surrounding unethical mining and also possible outbreak of civil war. And you can imagine that if a war were to break out in one of these countries that dominates the supply of a metal, then our supply could be severely impacted. Another example that we could look at are the rare earths. So we were talking before about those, and a lot of rare earths come out of China. And I believe in 2010, around 90% of rare earths were coming out of China. And again, this is problematic as it gives those countries that have the supply the kind of power to turn the supply on and off, a bit like a tap. And that can result in price rises. And that's what we saw in 2010. So China decided to reduce its supply of rare earths coming out, and prices skyrocketed as a result. And this causes like other countries, so maybe countries like the US or the European Union, etc. It causes them to think, okay, well, maybe we need to be looking elsewhere for our metals. And we're kind of seeing the effects of that now, where last year, I believe that China was only producing 60% compared to the 90% that it was producing 10 years ago.
Yeah, it's really interesting to hear it, because you completely see how it plays into like diplomacy and stuff, because if your only source of a particular element is that one country, then you don't want to, you don't want to make them angry, do you? You want to keep staying with them, exactly. so you can still, keep making your smartphones and whatnot. Now, there's an interesting question come in on Facebook. This one, I guess, if we know the makeup of the elements, could we not make synthetic or replica versions of them, the ones that we rely on the most for life? So I guess that would be, is that an alternative, rather than depending on this one source or having to look elsewhere, we could synthesize our own one that would be just as good?
We could synthesize things. I guess the only issue being would be that whether you're putting too much energy or even cost into producing these synthetic elements, that it's not cost effective to do. And it might be the case that instead it is actually just cheaper to go and mine them wherever that may be. But I don't know exactly how much it would cost for you to synthesize these different metals.
Yeah, I think a lot of it does come down to that, doesn't it? It's the cost, and at the moment doing that's really difficult, or there's a lot of research needed to get to that point, and at the moment it's just not viable economically, I suppose. But yeah, really interesting idea. That's a nice question. Thank you for that. So I really want to talk a little bit about you've talked about our demand for metals going up, and one of the growing sectors, and something that I think a lot of us are really pleased to see growing, is the whole area of green technology, solar panels, wind turbines, electric cars, all that kind of stuff that is going to transform, our society, reduce our carbon emissions, save the planet, all that kind of stuff. But these require metals, don't they? They don't just come out of nowhere. There's the building blocks to make these things require some of these resources that you've been talking about, don't they?
Yeah, exactly. And metals are an incredibly important part of the transition to renewable energy. If we take one metal, for example, if we look at copper, copper is important in renewable energy sources and also in conventional energy sources. But actually, if we look at the amount of copper that we need for renewables versus those of conventional sources, actually we need around 8 times more copper to produce the same amount of electricity. So you can see that there is kind of a trade-off between wanting to transition to a greener future and also needing to mine more. So it's an important consideration.
Yeah, I mean I'm quite stark. You think 8 times more copper to get the same amount of energy that we're currently getting through conventional sources. So there's definitely a trade-off there.
Yeah, exactly.
If you access to that stuff. So I guess if that means demand's going to go up, so we're going to have to, if we're not going to be able to synthesize our own equivalents, like one of our viewers suggested, then we're going to have to look elsewhere to do that, aren't we? Are we going to have to look further and dig deeper, I suppose?
Yeah, I mean, this is an important consideration as well. So what we have at the moment is that a lot of deposits that were previously discovered were located in kind of convenient places, or maybe they were quite close to the surface. And that's what we can see here. So this plot is showing the depth at which deposits were discovered at through time. And what we can see is that in the first half of the 20th century, a lot of deposits were being discovered close to the surface. Whereas as we move towards the present day, a lot are being discovered at greater depths. And this is obviously difficult. It's more difficult to find things that are located further underground. And it requires us to come up with more innovative ways of exploring for deposits. So maybe we would use techniques like geochemistry or geophysics. And I personally work in using geochemistry for exploration.
Right. And I just want to bring in a question here, Tom, from one of our viewers. This sort of relating to, as you say, if we're having to dig deeper, the amount of energy required to get there obviously goes up. It's a lot harder to get into these deep deposits. And this question came in from YouTube from Virgil. They're asking, in Sweden, there are experiments in using hydrogen gas to power steel making. Is this a viable solution to reduce the CO2 emissions from mining? Any similar projects elsewhere, would recycling work? So I guess, yeah, really concerned there about, are we able to reduce the emissions of the mining process itself? Because we appreciate it's so vital, but is there anything we can do there?
I mean, so I've not heard of this particular example, but it sounds like kind of an innovative way of trying to use some of the waste products that are associated with mining. And I have read about instances where mining companies have started to put more emphasis on using the waste products and turning them into something positive and something that we can use. In terms of that particular example, I've not heard of that. But I agree that moving forward, recycling of waste products is definitely a way that we can, try and reduce the environmental footprint of mining.
Yeah, absolutely. So I think that's going to be something that's going to focus a lot of minds over the years to come, as you say, as demand's going up. Now, tell us a little bit about your research specifically, because I know you're sort of very sort of interested in how we detect these deposits that we could then go and mine. So give us a little insight into that, and what's a sort of typical day like at the museum for you as well.
Okay, so here we have an image of some of the facilities that we have at the museum. This is an electron microprobe, and we use this to measure the chemistry of minerals. And that's a lot of what I do. So I use the chemistry of minerals, and I look for characteristics within those minerals that might indicate whether locations are likely to host an ore deposit or not. And I think it's kind of a bit like being a detective, except in the looking for clues, we're looking for clues within minerals. And obviously the reason for doing this is ultimately to locate deposits better and to ultimately reduce the amount of drilling that we're doing, which has obviously a monetary and also environmental cost to it. Yeah, no, it's really good to hear that we're trying to find ways to sort of minimize their impact on the environment, because it's acknowledging that we need these resources, but we don't want to dig up the entire planet to try and find them. So I guess it's sort of, I guess you're sort of trying to figure out, where do we actually focus our efforts and then start digging, in a sense. Yeah. Is that fair to say? Yeah, exactly. Yeah. So let's talk a little bit about the process of actually getting from a rock to, say, a piece of metal in your smartphone, because that, that's quite a leap, isn't it, from rock to, kind of consumer electronic device. I imagine there's a few stages in it. Could you maybe briefly talk us through broadly how that process works and how long it typically would take? So what we want to do is take our ore materials and subject them to several different processes. So these might be chemical, physical, electrical, and ultimately we want to increase the concentration of whatever the element is that we're interested in. And the first step always when we're doing this is to crush the rocks. And this is an incredibly energy intensive process. After we've crushed the rocks, so if we were to take, for example, what we do with copper in copper processing, we start out with something that's around 0.2% copper in it. And this stage is called froth flotation. So what we do is we take our ore materials, we add water, we add chemicals, and we add air. And essentially the chemicals make the ores hydrophobic, so afraid of water. and they float to the top, and we can scrape them off and separate them from waste material. What we have after that is a process that we call smelting. So we take that material from the previous process, we subject it to high temperatures, and we melt it, and then we pour off the molten metal into molds, which is what you're seeing here. And then again, this is also removing impurities. And finally, we have this process called electrowinning, which uses an electrical current to remove those final impurities that we have and leaves us with a product that's around 99.99% pure.
Wow, it's a fascinating process. I've never really seen that before. It's really interesting to kind of have you kind of talk us through those stages, and that process I guess takes a little bit of time to go from beginning to end.
Yeah, exactly.
Yeah, excellent. Well, it's been really fascinating to hear from you, and it's been really interesting, I think, to think about, you know, how we're striving for this green, sustainable future with you know, electric cars and solar panels and all the renewable energy and things like that. But it's really important, I think, and you've touched on that today, to consider how that technology actually works, how that's actually made, and how we get the materials to make that. And I think you'll definitely have given some people something to think about today. So thank you very much, Tom, for sharing that with me. And we've run out of time, unfortunately, but thanks very much. And I do hope everything goes well with the rest of your PhD.
Thank you.
Okay, thanks a lot, Tom. Bye now. And thank you guys as well for watching. Thank you very much for your questions as well. I hope you enjoyed that. I'm sure it's given you something to think about. It's definitely given me some stuff to think about. And you know, we want to have this greener future, but we've also got to consider how we actually make that happen with the technology that we need to do it. So lots to think about there. And thanks again to Tom for chatting to me today. If you enjoyed the show and would like to help us out, remember, it's been really tough for us this year at the museum. We've not been able to open for nearly a year. So any donations that you can manage, small or large, are greatly appreciated, and they really help us to continue. So thanks very much for those of you that have done that. Next time, we'll be taking a very different tack. We're going to be looking at penguins with my colleague Christina and curator of birds at the museum, Alex Bond. But until then, thank you so much for joining us today. All the best, and we'll see you again very soon.